Welcome to the San Francisco Amateur Astronomers. So glad you're all able to make it tonight. Just a couple announcements. I won't take too much time. We do have fun things coming up in the near future. We have a picnic coming up. Our annual summer picnic is not this Sunday, but the following. Check out the website for details, the calendar. I think we're already past the RSVP dates, but I bet if you talk nicely to me or Lisa, I think we'd be able to make something happen. So I'm Jason Griesbach. You can find me on Slack. Other things going on. We do have a members-only star party this weekend, which you've hopefully already RSVP'd for if you plan to attend. There will be no lecture in August. I'll be traveling and I'm having to search for a sub-in, but if you're offering to be a sub-in and on occasional lectures, let me know. And what other things do we have coming up? I think that pretty well covers it. We're very pleased to have Dr. Clark with us today. We had a very enjoyable dinner with her beforehand, getting to know her. Her adventures of hiking with her husband and 1-year-old, which is an adventure in and of itself.
Yes.
Very inspiring story about how she got into astronomy. It's where she was able to get a job. but I know that she's going to give a fantastic lecture, seeing the universe through a magnetic lens, if you will. I think it's going to be phenomenal. So without further ado, Dr. Clark, thank you.
Thank you so much. Thank you so much for having me. It's really a pleasure to be here, and I've really been looking forward to coming here and telling you a little bit about what I like to think about, which is the stuff between the stars, the interstellar medium. I'm Susan Clark. I'm an assistant professor at Stanford and have lived in the area for about 5 years now, but this is my first time here in this very cool museum, so thank you for the excuse to come down here. And my first time, of course, meeting and talking with you all. So I understand that this tends to be a fairly technical audience, but also that there's a pretty wide range of expertise. So I've tried to put a little something for everyone in here. We'll see if I hit the mark. But please feel very free to interrupt, to ask me questions during, to tell me, explain that again, or we know all this, go faster, or whatever it is that you would like.
Raise your hands if you're experts.
Yeah, fantastic. Okay, I'm very pleased to be here with you all today. And I know that you are all astronomers, which means you are skilled at finding dark regions of the surface of the Earth to go and look up at the sky, or at least this is something we all probably aspire to spend more of our time doing. And when you look up, if you're privileged enough to get away from the city lights and look up at the sky on a dark night, you behold all of these wonderful, dazzling points of light from stars in our own home galaxy, the Milky Way. And if you've gotten to a place that is dark enough, you've probably also beheld these sort of dark lanes across the brightest swath of stars that is this midplane of our Milky Way galaxy. And that might have been your first clue in the optical wavelengths that we're stuck with our own human eyes. That might have been your first clue that there's something else out there other than the stars themselves that we can actually see and perceive. That darkness is not an absence of stars, right? It's actually the presence of interstellar dust. This interstellar dust is one of the components of what we creatively call the interstellar medium. Literally, the stuff between the stars. Astronomers tend to abbreviate this the ISM. So this is the real beating heart of much of my research program is to study the ISM, the interstellar medium. And even though this is this fascinating medium that I love and have devoted a good fraction of my life to understanding, it's sort of a weird name, right? literally it's named for what it is not. It's just the not stars medium, which I always joke is like an oceanographer referring to it as the stuff between the whales, right? That's a very strange name to call this incredibly important environment that we would like to study and understand. And it's particularly weird, actually, because the interstellar medium is even more deeply linked to the stars than even the ocean is to the whales. It is quite literally the stuff that new stars are born out of. And so sometimes we like to describe the physics of the gas and dust and the evolution of the interstellar medium as a sort of stellar life cycle. That this gas and dust that make up the ISM is the material that is able somehow, in ways that we would like to understand better, to transition in regions from being very warm, diffuse gas or very hot plasma into little pockets of very cold, very dense regions of interstellar space. They get cold and dense enough that they actually can be the sites of the formation of molecules, even complex molecules. These are the regions that we call molecular clouds, and some pockets of those are able, one way or another, to collapse gravitationally under their own weight and form new baby stars and planets. And then those stars, of course, live out their lives within this dramatic interstellar environment swirling all around them. And they interact with the interstellar medium. So stars are constantly sort of gently sloughing off stellar wind. Some of the most massive stars very dramatically explode at the end of their lives in what we call supernovae. And these processes feed energy and momentum and literally material stuff back into the interstellar medium, back into the stuff between the stars, and becomes the seed for future cycles of stellar birth. And so we can think of this as a little bit of a life cycle. I thought I would give you this high-level motivation for why you might care about the interstellar medium if you are a star person. But I'll also tell you my maybe slightly nerdier version of why this is a fascinating physics system. I am first and foremost a physicist. And that's because this material, this stuff that fills the space between stars and galaxies, is a very rich laboratory for studying physics on scales that we could just never hope to create in a laboratory at home. And what I mean by that in sort of big picture schematic terms is that all at once, if you want to understand the interstellar medium, which means if you want to understand the evolution of galaxies themselves, you need to care about scales as big as galaxies themselves, or larger even, all the way down to the surfaces of an individual little dust grain somewhere out there in interstellar space. The physics of what drives the evolution of this environment really is connected across that bewildering range of scales. And that to me is just invigorating, I suppose. Challenging and exciting. And so I thought maybe we would start our talk here just a little bit closer to home. My particular research, much of it is concerned with astrophysical magnetic fields. And that's probably what's most familiar to most of us astrophysically in the context of the Earth's magnetic field, right? This is what turns the needle on your compass, if that's what you're using to navigate, perhaps not these days. And yes, good, an animation. You may know that the planetary magnetic field is very helpful for us, for life on the surface of the Earth. It among other things, helps the Earth retain its atmosphere. It helps it not get stripped away by the solar wind that is constantly coming at us from our own sun. Magnetic fields in general are generated by motions of charged particles, and so in the case of the Earth and planetary magnetic fields, it's really the motion of convective motions and the rotation of the Earth that, because we have a liquid metal outer core in our planet, are able to sustain this planetary magnetic field in a mechanism that we call a dynamo. The sun, of course, also has a magnetic field, which is the source of all sorts of fascinating and quite beautiful magnetic activity. Sun. I was learning a bit at dinner today that some of you are very skilled at solar photography, or have traveled or will travel to see the northern lights at some point. And so magnetic phenomena abound that it seems that this crowd is familiar with and able to capture photographically, which is absolutely amazing to me. But possibly not at the forefront of your mind is that it's not just compact objects like stars and planets that are home to their own magnetic fields. There also exists an interstellar magnetic field. Galaxies themselves are home to large-scale coherent magnetic fields that are quite literally coherent, meaning ordered on some scale that is a decent fraction of the scale of the galaxy itself, if that makes sense. If it doesn't make sense, please tell me. This, by the way, I will tell you just a little bit about how it is that we actually measure magnetic fields at great distances in interstellar space. But just to show you, this is the Whirlpool galaxy, might be familiar, nearby Grand Design Spiral, so named because it has these beautiful spiral arms, and it's interacting with the nearby galaxy, so it's a subject of much fascination for many reasons. But the little yellow line segments on the right-hand panel here are showing you a visualization of some data that help us infer properties of the magnetic field of this galaxy itself. This is the magnetic field that exists in the diffuse plasma in the interstellar medium, in the space between the stars. And in recent years, we have made progress mapping magnetic fields in a host of different types of relatively nearby galaxies. And so some of these, I believe this, you might recognize from the image I submitted to advertise this talk. But you can see that we've been working on visualizing our data as these sort of swirls that indicate the orientation of the magnetic field, along with some beautiful Hubble images of these nearby galaxies. Okay, so from my perspective in my research program, I really want to understand how these magnetic fields are affecting the physics of what goes on in interstellar space. And so for me, I want to understand how magnetic fields affect these processes of forming new stars and forming the molecular clouds that form the stars in interstellar space. I want to understand the character of turbulent motions in the interstellar gas, which is fundamentally, intrinsically magnetic. And so again, a laboratory for something that we could just never build on Earth. Many people in astrophysics, for many different reasons, also want to understand how very high energy charged particles called cosmic rays, how they move through the galaxy and through intergalactic space. Because they're charged particles, they are strongly affected by the presence of these galactic magnetic fields. And so our fates are very much linked. If you want to understand the propagation of charged particles, you need to understand the magnetic field and really vice versa. But basic questions like what actually is the strength and structure of the magnetic field of the Milky Way are still very much open questions that we're still tackling from many different angles. So as a research topic, this is very rich and open, and in some ways it almost has a bit of not a bad reputation, but a reputation for being this thing that is so difficult that it's almost mean to ask someone a question. Like there's a little bit of a joke that if someone gives a whole nice lecture on their research and they haven't mentioned magnetic fields, the mean thing to do, or the thing to do if you really want to poke them, is to be like, what about magnetic fields? So, my goal is to not be that person. My goal is to talk to you so much about magnetic fields that you can't possibly get me with that one. So, you're probably wondering at this point how it is that from a data perspective we might even begin to tackle this question, right? How is it that we measure interstellar magnetic fields? Maybe as a child at some point you played around with some iron filings in a bar magnet, where you can plop down your bar magnet and watch your iron filings kind of pop into place and reveal the magnetic field of your magnet. We of course can't fly around interstellar space dumping iron filings out the back of our spacecraft, because interstellar space is very, very, very vast, and also because that would be littering. So instead, we're really, for the most part, stuck here. We have our telescopes on the surface of the Earth or very nearby in space, and we need to infer everything we can about astrophysical magnetic fields through light. That's really all we can do, is collect light in different wavelengths and figure out what we can. And it turns out that we can learn a good deal about interstellar magnetic fields through a property of light called polarization. And this is probably a very familiar property to you, maybe for many reasons, but one of them might be that your polarized sunglasses help you see on a bright day, specifically by transmitting only one polarization state of light preferentially. And so the polarization of light is this, if light is polarized, it has a preferential plane of propagation of the electromagnetic wave. And so light coming off of the sun is, for the most part, intrinsically unpolarized. It has no preferred direction of propagation. But light that has bounced off the surface of the road that you're driving on, or the nice lake or ocean that you are staring out at, light that has reflected off a surface like that picks up a preferential polarization horizontal to the ground. And so the reason you can see more clearly through your polarized lenses is that they preferentially transmit only the orthogonal polarization state of light, the vertically oriented polarization state. And so it reduces that glare. You just see less of the light that has bounced off of the ground. And this is very handy for a day at the beach, but this same basic property also lets us see magnetic fields, invisible magnetic fields, way out in the distant, diffuse reaches of interstellar space. And the reason that we can do this really comes back to those dark lanes that you can see on a dark night across the face of the disk of the Milky Way. Interstellar space contains a good deal of interstellar dust. when we say dust, we usually mean squiggle micron-sized chunks of material that just, in general, have a sort of amorphous, blobby shape. You know, it's not perfectly spherical. Little chunks of not perfectly spherical, solid matter. And this interstellar dust is everywhere, and it turns out tends to find a preferred alignment relative to this interstellar magnetic field that it's sitting in out there in space. And so I'm happy to talk your ear off about the physics of dust grain alignment if anyone is interested at some point. But the high level takeaway is that what tends to happen is that these little lumpy grains of dust tend to align their short axis parallel to the magnetic field they're sitting in, just on average, right? And so the fact that there's all of this dust sitting out there finding this preferential alignment means that even though light coming at us from distant stars is usually intrinsically unpolarized, unless it's a particular weird star, but usually starlight is unpolarized. If you observe those stars in optical wavelengths or in the near infrared, if you measure the polarization of the light coming off of those stars, you will measure an orientation of that polarization that doesn't actually have anything to do with the star itself. It was picked up by the light as it was filtered through all of this interstellar dust, because these little dust grains, all lined up in this particular way, tend to absorb one component of the polarization of light more than the other. And so what eventually makes its way to your telescope is light that has a polarization state that tells you about the interstellar magnetic field between us and that star. Does that make sense? I'm gonna look at your faces for comprehension. Perfect. And so it's really, we measure polarization in optical wavelengths, in the same wavelengths that you see with your eyes, or just a little bit redder than that often. And we are able to infer the orientation of the magnetic field out there in this interstellar dust. This is actually the way that the interstellar magnetic field was first experimentally confirmed. That happened in the 40s. Way back in the 70s, people were already starting to make maps like this. This is showing you a whole bunch of measurements at optical wavelengths and polarization toward a whole bunch of stars, where now you can see the mid-plane disk of the Milky Way galaxy here. You start to see sort of coherent structures. That is the interstellar magnetic field that you're starting to see emerge there from observing many different stars in optical polarization. There you go. And these dust grains have one more property that is enormously useful to us as astrophysicists. In addition to this selective absorption of light, these dust grains are also emitting their own thermal radiation. Just like stars are, just like planets are, just like you and I are, dust grains are emitting thermal radiation, and because they're lined up in this particular way, if you measure wavelengths of light that are sensitive to this thermal emission from dust, you will also measure that it is polarized, now in the opposite sense. So now as a 90-degree flip from what you measure in the starlight, you measure polarization, again, just imprinted by the fact that these little dust grains are magnetically aligned. And this is a tricky measurement to make, but very useful if you can do it. One of the best ways to do this is to measure polarization, linear polarization, polarization in the far infrared, because that's where this thermal emission from cold dust is quite bright. And so just to show you some really truly hot off the press data, this is from a paper by my graduate student, Caitlin Karpovich, that is quite literally in the refereeing process right now, but she's a real gift for data visualization. So these are data of a bunch of regions in the Milky Way that are forming new stars, a bunch of star-forming regions, where we've measured, or we and others, this is really us compiling data taken by many different observers, the orientation of the magnetic field traced by emission from the dust in these star-forming regions. And if you are curious how we measure polarization in the far infrared, the way these data were taken is from this instrument. Has anyone seen this before? Are you familiar with this particular observatory? This has been retired just recently. But this was SOFIA, the Stratospheric Observatory for Infrared Astronomy, is an acronym. I think this is one of the most wild concepts that I've laid eyes on. This is literally a converted Boeing 747 SP, I want to say, that they cut a hole out of the side of and put a telescope here and like made a little door that could open mid-flight. And then this thing would go fly around the stratosphere, open up the door, and observe. The reason for doing this, of course, is that if you want to observe at wavelengths like the far infrared, you would like to get above as much of the precipitable water vapor in the atmosphere as you can. And so, but it's cheaper to do it on an airplane than to launch your instrument into space, especially if you want your instrument to be able to come back to you every night and you make tweaks to it. And so this was this sort of wild concept, but this flew for a while and made a lot of measurements with an instrument called Hawk Plus that are exactly what we use to visualize or to measure the magnetic field structure of those star-forming regions. I had the immense pleasure of flying on SOFIA very, very shortly before it was retired forever. So there's me boarding the plane. You can squint at me. Of course, the better way to do this is to put your telescope in space rather than cut a hole in your airplane. And so very dramatic recent data of this polarized emission from interstellar dust was taken by the Planck satellite. This was a European Space Agency mission that flew not too long ago. And because it was in space, mapped the entire sky at a frequency of 353 gigahertz. That's, if you like to think in wavelength space, it's about 850 micron. It's a wavelength that is dominated by this thermal emission from dust in our own Milky Way. So this is an all sky image of data, meaning if you take the sphere of the sky and you project it onto a flat surface, in the same way you might take the surface of the Earth on a globe and then project it onto the flat surface of a map. This is exactly that, just a projection that shows you the sky looking in all directions. And the colors in this map are a visualization of essentially how much dust there is looking in different directions. And so the bright red here, this is again the midplane of the Milky Way, the pancake disk of the spiral galaxy that we live in. And then sort of up here and down here in the map are looking at the poles, the galactic poles, up away from the midplane disk of the galaxy. Of course, all from our perspective quite nearby Earth. But what's dramatic about this image is, of course, not the colors, it's these Van Gogh-like brushstroke swirls that you perceive. And that is showing you exactly a visualization of this inference that we can make from measuring the polarization of this light, the orientation of the magnetic field in the dust in interstellar space. This is, I would say, one of my favorite scientific images of the last decade or so, let's say. And these data have been enormously useful for me in particular. But I also want to acknowledge that some people are not so excited when they see this image. To some people, this is something much more horrifying. This is not my beautiful magnetic interstellar medium that lets me study the evolution of gas and dust and galaxies. To cosmologists, this is actually a very frightening foreground to very faint signatures of polarization that we would like to see imprinted in the very earliest light from the universe. And so you may be familiar that we can measure this relic radiation left over from the formation of the universe that we call the cosmic microwave background. This is the earliest light that we can directly measure with our telescopes today. And a major thrust of research worldwide is to measure the polarization of that light, of the cosmic microwave background light. Because encoded in that polarization of the light is really actually all sorts of fascinating physics, but potentially some information from an even earlier epoch, from the very first instant, the first trillionth of a billionth of a second after the Big Bang, when we believe that the universe underwent this period of extremely rapid expansion called inflation. Long story short, we should theoretically be able to get more information about that very early moment of the universe's existence from the polarization of the cosmic microwave background. But it turns out that at these same wavelengths where we are trying to make that measurement, there also exists this very bright emission from dust in our own Milky Way. It's really the age-old saying that one person's treasure is another person's foreground. We use foreground to mean literally a contaminant that is in between, that is in between us and the beginning of the universe, but very similar to a background conceptually, just contaminating stuff that you don't want, but that I very much want and treasure. And so this is just to complete the story for you. It's also the case that radiation from high-energy particles, charged particles that are accelerated in the galaxy's magnetic field, also emit polarized radiation that is also a foreground for this signal. So the takeaway is that we all need to work together, right? The better we can understand the interstellar medium and its interaction with the stuff and the magnetic fields in the galaxies, the better we'll be able to do what we like to illustrate in cartoons, which is strip away the contaminating foregrounds and reveal the cosmic microwave background beneath. And so this is the reason that a reason that I actually collaborate on large cosmology experiments. You might not have expected it from me saying that the core of my research is interstellar physics and astrophysical magnetic fields. But actually next week I'm going to be in Toronto at a collaboration meeting of the Simons Observatory, this new large sort of forefront observatory that is measuring precisely this, the polarization of the cosmic microwave background, and this polarized emission from material in our own Milky Way galaxy. This is the site in the Atacama Desert of Chile. And so, quite literally, we are working together. We're going to do very cool galactic science with by collaborating, hopefully this will also help us separate that foreground from the faint cosmological signals that we would all like to uncover. Okay, I thought that I would also just mention to you briefly that we have other ways as well of tracing magnetic fields in interstellar space. So well, I am not a great artist, but here are my little cartoons. I have talked to you quite a bit about how we can measure interstellar magnetic fields through the presence of interstellar dust. It imprints this signal on the polarization of background stars, and we can measure the thermal emission of those dust grains, and both of those help us measure magnetic fields in the sort of dusty, neutral medium of the galaxy. Just briefly, in case this piques anyone's interest, we have a few other techniques that are also quite useful. If you have linearly polarized light and it passes through a magnetized plasma, and much of interstellar space is quite literally a magnetized plasma, the polarization angle of that light will rotate as it traverses that medium. And this is called Faraday rotation, and it's something we can actually measure in the radio wavelengths. And I mentioned briefly that charged particles accelerated by the galactic magnetic field also produce this bright polarized emission. That's called synchrotron radiation. We can also measure that. And so you might think that this is actually quite an easy area of study. Look at all of these different tools of the trade that we have to put the story together. But of course, one of the tricky things about these types of data is, first of all, they can be difficult to gather. And second of all, they're each just telling you kind of a piece of the puzzle. And it remains to be done to put them together to understand the whole. And so each of these is tracing sort of different environments within this very complex interstellar medium. And they also are usually giving you information on only one component of the three-dimensional magnetic field. So I have just a few minutes left here, but I think I want to tell you just a little bit more about what I have been excited about recently, which has to do with measuring properties of interstellar gas. So I showed you Sophia, a telescope that has since been retired. Now I'm showing you Arecibo, which was the largest radio telescope in the world until until a larger one was built, but it also tragically collapsed just a few years ago. I don't know why this happens to telescopes that I love. But this was a large and very wonderful radio telescope in Puerto Rico that made many exciting, important discoveries, but among other things, with this massive dish, was able to make very sensitive observations of emission from atomic hydrogen in interstellar space. Just if you're curious and you like to think about different emission lines that we're able to measure in different wavelengths, atomic hydrogen is just one proton and one electron. Those two have quantum mechanical spins. They can be aligned or anti-aligned. The transition between aligned and anti-aligned has a characteristic energy that corresponds to a photon with a wavelength of about 21 centimeters. So we call this emission from this ground state atomic hydrogen the 21 centimeter line. Creative. And 21 centimeters, of course, is in the radio portion of the electromagnetic spectrum, and it's very helpful to have a massive dish of collecting area if you want to make very sensitive measurements of it. The intensity of your emission line, let's say, as a function of wavelength. And if you're looking at a particular line, a particular emission line, meaning some particular transition, atomic or molecular transition, the wavelength tells you something about the Doppler shifted velocity relative to you, right? You can shift back and forth in wavelength space just via a Doppler shift from your relative motion between the blob of gas out there in space and you with your telescope. So we measure some intensity as a function of wavelength. Often we're measuring emission, sometimes we measure some absorption line, but this is sort of the fundamental dimensionality of the problem that we're working with, these squiggles. And in particular, one thing that we often want to understand is the temperature of the gas. One of the amazing and difficult things about the interstellar medium is that it spans this just bewildering range of physical states, very, very hot plasma, and you also have these very, very cold, like 10 Kelvin, molecular clouds that are forming stars. How does gas transition between those is an outstanding question. And so often you want to take your emission line and you want to learn something about the temperature of the gas, basically by the width of the line, because the hotter the gas is, the more the atoms are moving around, and the more that's sort of spreading out the emission in wavelength space. That make sense? Yeah. And so people, write beautiful papers with panels like this, like panel upon panel of all of these squiggles. And there's a lot of information in that. But we don't have to work just one sightline at a time. We can also image the sky and measure emission as a function of wavelength. We can measure in 3 dimensions, basically. This is that 21 centimeter emission. This is emission from atomic hydrogen in our own Milky Way galaxy, imaged by the Arecibo telescope before it collapsed. And this is 3-dimensional, this is a movie of data. It's 3 dimensions, right? The spatial dimensions here on your screen are just the sky as viewed overhead of Puerto Rico. Literally, from the bottom to the top of your screen, that's about the declination range of the sky that you can see from Puerto Rico. And then the movie is panning, and that's just the Earth turning and the sky moving overhead, okay? And then you also have this depth that you perceive in the movie. And that's moving you back and forth in wavelength space. That's moving you back and forth and basically showing you gas moving at different relative velocities relative to us. And so this is the thing that I've been kind of obsessed with recently. It is like, how do we use the richness of our data? I mean, really use it. Not these classical methods that would take just one sightline along this. Not taking this beautiful 3-dimensional data and skewering it to make one squiggle, right? And also not slicing it the other way to just make one image. How do we actually use the 3D-ness of these data to learn more about the physics of what lives within it? And so I'm just going to quickly flash for you that we have come up with creative ways to use the structure in the 3D data that we have, to use the shape information, the image space structure, to do what people have traditionally done with the width of the squiggles, to separate this emission into what's coming from the warm stuff and what's coming from the colder pockets of material. And we've found that we really can interpret what it is physically about the structure of this gas that separates it into warmer or colder components. And we found that the colder, stringier, more filamentary bits of this data portions of this emission are actually aligned with the interstellar magnetic field. And so this is another brushstroke technique where the brushstrokes on the top panel here are actually not polarization data at all. This is showing you the orientation of linear structure, stringy little filaments of neutral gas in our galaxy, that it turns out is statistically very tightly coupled to the structure of the magnetic field that it is sitting in. And I think I want to, there you go. So this is the thing I can't stop thinking about. There is information in the spatial structure of the data, if we can just come up with clever ways to decode it. And I think that is the note that I want to end on so that I don't go too long here. But so the next time you find yourself away from city lights and you're looking up on a dark night, my hope is that you'll think about all the stuff between the stars and all the stuff you can't see with your eyes, right? All of this very rich environment of interstellar gas, interstellar dust, interstellar magnetic fields, all interacting in complicated ways, but imprinting clues out there on the light that we can gather that actually let us decode the physics of what's going on. Thank you.
Time for questions.
Please.
So, do we know what effect these interstellar galactic fields have on, say, star formation? Do they affect star formation? Are they as a result of the movement of material, say, in the spiral arms of galaxies? And also, are they weaker in older galaxies, such as elliptical galaxies, than they would be in a more active galaxy?
Yes. That's a fantastic question. The easy part is the last one. Yes, in general. Although our ability to measure the magnetic field strength is actually one of the trickiest parts of this whole endeavor. But in general, yes, you don't see those same structured, coherent, generally stronger magnetic fields in ellipticals as you do in spirals, for example. And the question of how magnetic fields affect star formation is very hotly debated. The answer, as I would summarize the field's understanding right now, is that it's complicated. The old picture a few decades ago was that the magnetic field actually ruled it all in terms of star formation. That actually, as you started to coalesce material into what would become a protostar eventually, as you bring material together, you do condense that material and you strengthen the magnetic field by basically pushing those field lines together. And what that means is that you can build up a very strong magnetic field that would support gas against further collapse and stop the formation of stars. And so actually the story for a long time was that, well, because that effect is so strong, you would support gas against collapse until that gas had hung around long enough for the more neutral component of the gas to physically decouple from the ionized component of the gas. Because it's really only the ionized component that's directly coupled to the magnetic field, and it is transmitting that to the neutral stuff collisionally, because they're all just sort of bouncing around together. And so the old story was really that you would then wait around for the neutrals to slowly slip away from the ionized component of the gas until you had enough neutral material that it would collapse, form a star. And so it really was that there should be, that theory predicts that there should exist these long-lived, magnetically supported little clouds that are not able yet to form stars because the time scale for that process is pretty long. And then people went, actually, with Arecibo, that telescope played a big role in this, and they measured the field strength toward a bunch of molecular clouds. And it turns out that this picture doesn't really hold up to the data. And so now we think it's actually a much more complicated story, that at some scales and in some environments, the presence of the magnetic field is maybe accelerating star formation or able to bring material together, and at some scales it's inhibiting star formation and supporting it against collapse. But the field has gone from this simple cartoon you could put in a textbook and say, see, to actually it's very confusing and complicated and depends on the scale and environment. So perhaps some clarity will emerge out of that soup with more data soon. That's a great question. Oh, please.
You said that towards the end that it was like the stringier, colder molecular hydrogen that aligned itself with these magnetic fields. Why is it only the colder one?
Great question. I would also like to know. My picture here is that when that colder gas forms, when some of that atomic hydrogen cools to sort of transition to the state of being colder gas. Anyway, there's a whole wonderful physics, but it turns out that atomic hydrogen tends to move toward being either warm or cold, and if it's in between, it's probably because it's recently been kicked out of being cold or being warm, if that makes sense. Anyway, my thinking currently is that as it is going through this thermal transition to become colder, motions in the gas are probably stretching it along the existing magnetic field lines, and or the magnetic field itself might be strengthened in this process of forming the colder stuff out of the warmer stuff, if that makes sense. I think at this moment, what we have are some intriguing new observational facts that we need to theoretically explain better. Yeah, this is a great question. Yes?
You were talking about how linear mass structures are colder and how the magnetic field kind of seems to be permeating throughout the Milky Way, at least for most galaxies. Is it possible that the magnetic structure can explain how galaxies have their own structure, like for example, spiral galaxy or different types of galaxies? And could it also explain why galaxies tend to be like just one plane instead of more like a spherical?
Oh, it's a fantastic question. It is probably the other way around, actually, that, in other words, it is probably more that the gas is dragging the magnetic field into that configuration at the time of formation of the galaxy than that the magnetic field is specifically imprinting that geometric structure. But one of the things we'd like to understand better is exactly how galaxies build up their magnetic fields at the time of their formation, how their magnetic fields grow through some sort of galaxy-scale dynamo, and why it is that they end up with the strength and structure that we observe them to have today. And yeah, it's really still a very open theoretical question. It's tricky, by the way. I talked a lot about what's tricky about the data, why it's tricky to make the measurements that we do that give us observational information about this. Another big area of astrophysics is to use numerical simulations to study the physics of these processes. And it's also tricky numerically. It's very expensive to include magnetic fields properly in your simulations. And this can be especially true if you want to do a very large-scale simulation, like a so-called cosmological simulation, where you have many galaxies forming within your simulated volume. And so, you know, when I joked about it having a bit of a bad reputation, this is also quite true in the numerical simulation framework as well. So we're making progress, but yeah, exactly how the magnetic fields build up is very open. Great question. Yes.
So what instruments do you use to collect your data? What part of the electromagnetic spectrum does your data lie in?
Yes, okay, fantastic. I work with radio data for gas emission, gas absorption, also for measuring this effect called the Zeeman effect that gives you direct information on the magnetic field strength. A lot of that is in the radio. I also love everything from the far infrared to the sort of millimeter, submillimeter, where we can measure this polarized thermal dust emission. So everything from the wavelengths that these cosmological experiments are going after, to the higher frequencies where the dust is even brighter in the far infrared. I love the optical because we can measure starlight polarization, and we can measure other absorption lines between us and the stars that start to give us three-dimensional information about the distribution of material. Yeah, I am really not one of those astronomers that stakes my claim on a particular part of the electromagnetic spectrum. I'm more trying to grab from all of it and put the pieces together.
So are the signals in different sections of the electromagnetic spectrum, are they coherent?
They're giving you different pieces of information, but they can be tracing, they can be clues to the same puzzle, if that makes sense. Yeah, so often, you know, I think I'm sort of drawn to problems where you have to be a little bit clever about putting the pieces together. It's just an exciting way of working for me. So I like to think about, you know, how do I take my gas emission in the radio and my dust polarization in the far infrared and put those things together to understand how the magnetic field is influencing the gas, for example.
Did they give you a coherent story then?
Yeah, anyway, that's the goal, yes. Yes, exactly. You can figure out when they are a coherent story, yeah.
So, I don't have a question, I have a story.
Okay.
But I want to know if you have an explanation for it and if it ties into what you're talking about.
Okay.
I was in the garage one day, I had to grind a bolt, so as one does, grind, sparks. And at the end of this, I dumped out the grinder, the catch wheel, thinking I was gonna dump out a pile of metal dust. I didn't get metal dust, I didn't get a clump of semi-molten metal. I got this beautiful tree-like 3D sculpture of metal filings that were all clumped together, magnetically malleable but clearly magnetic.
Huh.
Even though I started out with a non-magnetic bolt, and I don't really understand what happened there.
Okay. Well, was this some sort of paramagnetic material? I mean, it sounds like it must
It
have
was
been.
metal.
Yeah.
So all I could assume is that once it formed bright sparks, the
You put a current through
things
it.
could
and it-
not
and it-
literally, but things could align.
Yeah.
Maybe it was the motor that was giving off magnetic
It
fields when
must-
things aligned.
Yeah, you must have driven enough of a current through it to impart a
It's a
magnetic field.
postdoc opportunity.
Yeah. Go for it.
If you could build any kind of instrument or had any access to any kind of instrument that doesn't exist currently, what would that be?
Oh, this is such a good question. It's such a hard question. Okay. Oh my god, how do I pick one? Oh no. one thing I have gotten really excited about lately, we have gotten a lot better in the last 10-ish, 10 to 15 years at measuring the distances to stars, which sounds like such a basic thing. I mean, astronomers have been measuring distances to stars for a very long time, but not that well and not that far from us. Recently, we've made really good progress at measuring stellar distances very precisely, which is exciting for me because I would like to see the interstellar medium not in this 2D projection. I would like to see in 3 spatial dimensions, right? I would like to understand how this stuff is distributed along the distance axis from us. It's enormously important for figuring out the physics, right? And so the fact that we can measure the distances to all these stars super well gives you an amazing handle on that, actually. Because if you can measure some property of the starlight that is affected, that is imprinted by the interstellar stuff, right? Now suddenly, you can start to solve the problem of how that's distributed in 3D space. So if you can measure how the dust is extincting or reddening the starlight, 2 things that dust does to the stars behind it, now you can start to see how that dust is distributed in 3D. And if you measure this polarization toward that starlight, now you can start to see how the magnetic field is structured in 3D. One thing I would love is to have a survey at near infrared wavelengths in polarization. So basically a wavelengths where you can see through more of the dust than you can in the optical, but to have preferably billions of high sensitivity measurements of the polarization of stars, because if we had that and there were no distances, we could start to do really cool inference of the 3D structure, 3 spatial dimensional structure of the magnetic field in ways that we never had before. So that's like one of my 12 answers to your question. Thank you. Yes, sorry.
So you mentioned earlier that it's been hard to measure the magnetic field of the cosmic microwave background because of what's covering it. So I'm wondering, has it, at like much grander scales than just the galaxy, are there measurable magnetic fields that we've been able to like measure and look at, and like what kind of influence that they have on a much larger scale in the universe?
Oh yes, okay, awesome question. Yes, probably the most dramatic answer to that is that galaxy clusters, so massive collections of galaxies that live in very overdense regions of the universe in terms of the universe's dark matter distribution. Galaxy clusters have diffuse material that we call the intercluster medium. Okay, so you've got your interstellar medium, and then the stuff between the galaxies we call the intergalactic medium. And then if you're talking about the galaxy cluster, there's also an intercluster medium that you can study. We have made measurements of the magnetic field and inferences of the magnetic field strength in those galaxy clusters that is surprisingly strong, is the short description of that. The intergalactic medium is really the grandest scale that we're going after in terms of the length scale, right? And that is very tricky because the magnetic fields in the intergalactic medium are fairly weak. I mean, weaker than the interstellar medium magnetic field. And I don't even think I mentioned the strength of the magnetic field that we're talking about here, but for the magnetic field in the interstellar medium for just nearby Milky Way, we're talking about 1 part in a million of the Earth's magnetic field. Okay, so we're talking about like micro-Gauss magnetic field, if that means anything to you. Nano-Tesla, if you prefer Tesla.
Is there
Yeah.
ever situations in which the magnetic field is like stronger than a gravitational pull at certain
to the diffuse plasma, essentially. Yeah. Right, because it really is, you really can't answer that question until you're talking about a specific length scale. But yeah, it can be dynamically improved. Let's see, wait, who's not asked a question yet? I can't tell if you're raising your hand. No. Okay, go for it.
Has there been any attempt to determine if, are all, okay, my question, are all these magnetic fields as a result of the existence of matter? So let's say in a large part of the universe where there's a giant void, with
Yeah.
galaxies around, are there any inherent magnetic fields, very weak or whatever, that may be present because of dark energy or something? It's very speculative.
No, it's a perfect question. This is why it's so important to try to measure the magnetic field, or at least put some limits in things like voids, in very, very empty regions of space that haven't been sort of polluted by the magnetic fields that were strengthened within galaxies. Because we don't know, it is again an open question actually, whether the initial, we call it magnetogenesis, like the initial genesis of the first magnetic fields in the universe, whether that, like when that happened in the history of the universe, it is possible that it was some symmetry breaking process in the very, very, very early universe, or you know, this epoch of inflation era of a very early universe. Or it's possible that you know, you had to wait until structure formation to really start to coherently build up magnetic fields. So this is putting limits, at least, on the magnetic field strength in voids is exactly how people are trying to answer that question. Also, they're trying to do, you know, numerical simulations and theoretical work and so forth.
Let's take 2 more questions.
Go for it.
So the interstellar medium is where 80% of the mass of the universe lives in the form of dark matter. Do you see any evidence or hints in your data that it either hinders or helps, or it somehow makes it gives you even any remote hope of detecting?
Okay, so I like to think of dark matter as sort of setting the very large-scale gravitational stage for everything that I like to study in the normal matter between the stars. I should have shown you a pie chart actually, but as you say, you know, it's only 5% of the universe is this normal baryonic matter. And then of that 5%, really only about 7% of it is in stars. So here, everything we've been talking about, the interstellar medium and intergalactic medium, all that diffuse gas in the universe, that is the other stuff that make up that 5% of so-called normal matter in the universe. So that's one answer to your question, is that the you know, your sort of large-scale gravitational environment is really dominated by dark matter, but then it's the physics of what happens to all of the gas and the dust within the big lump of dark matter that our galaxy lives in, that is our subject of exploration here. You know, and just very briefly, another answer to your question is that there are some theories of dark matter that could be observable by the creation of photons, well, basically an interaction that dark matter would produce photons when it interacts with a magnetic field. And so there are some people that are in a laboratory actually trying to test these theories of dark matter using strong magnets. And there are some people thinking about how we could use astrophysical magnets, astrophysical magnetism, to do other searches, tests for that sort of axion, like dark matter is what this is called. For that, the Milky Way's magnetic field is unfortunately probably too weak, or at least I can't think of any good ways to really use it. But there are people thinking about magnetic fields, the very strong magnetic fields that you can have in stellar remnants, compact objects like pulsars and magnetars. maybe you can think of clever ways to look for these sorts of interactions around objects like those. Tricky thing there is you have to understand their intrinsic magnetic fields quite well, and that's also a very open area of research.
Okay.
Please.
Last one.
How does AI facilitate your research? Does AI more like a way to accelerate your research or also transform your research?
Yeah, absolutely. I mean, as I said, I'm drawn to these problems where I like to use all of the data I can get my hands on and in clever new ways. And lately that has meant, in particular, using a lot of the technology behind AI, using big GPU clusters and using differentiable codes and so forth. To think about problems in new ways and at new scales, at scales that would have been sort of prohibitively expensive before, but tackling them in faster and better now. That's one way of answering that question. We actually are very actively thinking at Stanford, as you might imagine, about where those problems are ripe, like where my big picture astrophysics questions can meet with new AI-driven or just new methodologies to do something quite new and innovative. And we have a new Center for Decoding the Universe at Stanford. We're about a year and a half old. I'm one of the co-directors of it. And really, this is our purpose. It's to bring together the physicists like me, my colleagues in computer science and in electrical engineering and statistics, and really all across campus, to find those ways where if we just get over the language barrier, we can really make some magic by combining our expertise. So that's been a lot of fun the last few years.
Can I ask, where do you think I get the best view of the galaxy in the United States?
In the United States? Oh my gosh, everyone in this room is probably better at that than me. I think I've personally had the best views in like eastern Nevada. And I don't know, just anywhere you can get super remote. You can look for dark sky, designated dark sky areas. I went to Great Basin National Park once, it was like phenomenal. But I'm sure many people have better answers than I do.
Mount Tam at the members only star party. The Center for Decoding the Universe.
That's right.
I
Cool name, right?
love it.
Yeah.
Thank you so much.
Thank you so much.
And that was phenomenal. If you have questions afterwards, feel free to come over and talk.
Yeah, please.
You all have a very good night. Thank you.
Thank you so much.